magnitude, we're going to reconsider the 18 gauge wire, the previous example, where we found that it had a cross-sectional area of 8.2 times 10 to the minus 7 square meters. Again, the wire carries a current of 1.67 amps. And in part A, we're going to find the electric field magnitude in the wire. In part B, we're going to find the potential difference between 2 points on the wire that are 50 meters apart. And finally, in part C, we're going to find the resistance of this 50-meter long segment of wire. So let's begin with the equations we'll need for the problem. The first equation is 25.5, which gives us a relationship between the electric field in the wire and its current density, J. And in fact, this electric field is one of our target variables. In equation 25.10, given here, we get a relationship between the resistance in a segment of the wire and this resistivity in terms of the length of that segment and the cross-sectional area of that segment. And finally, we'll need equation 25.11, a very important equation in this chapter, which gives us the potential drop along the length of a wire in terms of the current flowing through the wire and the resistance of that length of wire. This is sometimes known as Ohm's law. And we obtain the resistivity of copper from table 25.1 as given here. So we're ready to begin with part A. The electric field, rearranging the first equation, is just rho times J, and J is I over the cross-sectional area. Putting in the numbers, we get 0.035 volts per meter. The potential difference along a length of wire of length L, 50 meters, is simply the electric field times the length of the wire, and that's going to be 1.75 volts. The resistance of the wire is the resistivity times the length of the segment divided by the cross-sectional area of the segment. And again, the length is 50 meters, and putting in the numbers, we get 1.05 ohms. We could have also written the resistance as the voltage along that length of segment of wire divided by the current flowing through the segment, and we get the same number, of course, 1.05